All right. So now, let's say we're trying to find a pixel in a movie, like a 10-second, let's say half a second movie clip. All right. We want to see if any of these have a black pixel. Okay. So a half a second movie clip, right? We're doing how many frames a second, right? We're doing 60 frames a second or something in a movie clip. And so a half a second is 30 frames. So we have 30 frames, which is the same thing as 30 pictures, okay? Or something like that, right? Or in general, in the general case where we don't know the number of pictures, we have n pictures, okay? And we can also say that we have n plus r height, right? And n plus k width, which is where r and k are just numbers we can do to make this to make this all work out. So we can write everything in terms of n, okay? And then in that case, right? So r and k can be any number, all right? And so in that case, as you might guess, well, we're going to, so every picture has this going on, and we're doing it that many times. So you might imagine that our first term is going to be that, okay? And if we say k equals 0 and r equals 0, you might imagine that we're doing a cubic relationship, all right? And any of you remember the cubic relationship? It comes up and then goes up even more crazier than the parabolic relationship, okay? And so that's another one, right? And we could keep on doing this. We could say, well, now instead of just one movie clip, we can have n movie clips. So we have n movie clips and n pictures in each movie clip, right? So n plus q, just another variable, right, to put pictures in terms of the number of movie clips. And we have n movie clips, right? And then all of a sudden we're going to have, how many do we have to search through to find the black pixel? Well, we just have to multiply all these stuff together, and we're going to get n to the power of 4th, which is going to be, you know, an even steeper curve as n goes to infinity, all right? And so as the n space increases, the number of things we have to search through increases by that much. As n space increases, the number of things we have to search through increases by this much, okay? In this case, we have 3 degrees of freedom, right? We have the number of pictures, right? The x value and y values, okay? And then when we add the number of movies, there's all these different movies, all right? And each one has a number of pictures and width and height. Well, now we're getting into n to the power of 4, all right? So now our space is getting much bigger every time we add a movie, which makes sense because every movie we're adding is adding, pictures, and every picture we're adding is adding x and y, right? The space is increasing kind of, drastically every time we add a movie. All right, so let's now we now know enough to talk about big O, okay? A little more clearly. So big O, the tenets of big O, okay, is we literally we call, or we identify the runtime of an algorithm based on the order of the number of things we have to search through as n increases. All right? So if the number of things we have to search through as n increases is n plus 3 or 5n plus 3, what we're going to do is we're just going to look at n and say, well, that's of the order of n, and so we're going to call it O of n. Okay? So just find the n, and then you know what the order is. Okay? And if the number of things we have to search through, right, in our other example, our picture example was n and n plus m. Okay, well, that equals n squared plus nm. All right? And the order of this equation, well, it's n squared, right? So we could say that's n squared, and that means it's O of n squared. Okay? That means that if I have something that increases with n or increases 5n plus 3, they're both going to be in this class of algorithms we call linear runtime algorithms. Okay? O of n. Even though you're looking at this and saying, oh no, they look slightly different. They do. But they're in this general class, and everything in that general class increases linearly as the search space increases. Okay? So it increases linear with the search space. And everything in this class of algorithms, right, even if m is 0 or m is 90,000, right, increases with that, with a squared relationship to the search space. So the number of things we have to search through as n increases will increase on the order of n squared. Okay? So all of those algorithms we're going to group together and say they're basically the same. And so if we have two different algorithms, one that's O of n and one that's O of n squared, well, and we want to say what happens when n gets really large, which algorithm do we expect to run faster? Well, it'll be this one, because it's not growing as fast as this one as n gets larger. Okay, that third situation with the, right, as you might imagine, that's going to be O of n cubed, and the fourth situation is going to be O of n to the fourth, right? This is the movie, number of movies is a degree of freedom, number of pictures is a degree of freedom, and then width and height are degrees of freedom. Okay? Are all degrees of freedom. Okay? So they all are things that can change. Okay? If they can't change, if they're constant, if it's always going to be 6 movies, that doesn't matter anymore, right? If it's not something that we're going to change, all right, then, or that can change, then it's not a degree of freedom. We don't have to worry about it. Okay, so if it's always going to be 6 movies, then that changes this O of n to the fourth algorithm to an O of n cubed algorithm, because we're going to have 4 times n cubed, right? 4 movies, times it by 4 movies, right? No matter what, we're not going to have more than 4 movies. And so we will say, well, that's on the order of n cubed. It's not going to change how big n is. I mean, at the order of n in that case. All right? So it has to be a degree of freedom. It has to be something that might be changed. All right. So one last kind of, or 2 last kind of videos. I know I said that last time, but we'll have 2 more. This is good, though. We'll take it nice and easy.